Hi, in this video I'm going to go over the solutions to the quiz you had over 5.1 and 5.2. And the first part of the quiz is the 20 multiple choice. And as I've mentioned, IB expects you to do multiple choice questions without the use of a calculator, without a data booklet, and in about a minute's time or less. So usually there should be some answers you can quickly eliminate and some shortcuts you can take if there appears to be calculations. So I'm going to just try and share with you my strategies for going through these first 20 multiple choice questions. Question number 1, which statements are correct for an endothermic reaction? So in my head, I immediately think of the little graph I sketched off to the right here, that the reactants have less potential energy and the products have more potential energy. So the system absorbs heat. Yes, that has to be true because the potential energy increases for the products. The enthalpy change is positive. That's also true for endothermic reactions. Increased energy is considered a positive change and decrease is considered negative. And then number 3, the bond enthalpy total for the reactants is greater than for the products. And this one's a little bit tricky, and it's a no, because bond enthalpy is really the energy, the potential energy. So if we look at it, the products are definitely at a higher level here, so it's less energy in the reactants since energy is being absorbed. So bond enthalpy is increasing for the products. So A, 1 and 2 only would be true. Number 2, what energy changes occur when chemical bonds are formed? So bond forming is exothermic, that's the product side of things. And when they're broken, that's the endothermic part. Reactants, the bonds have to be broken before the reaction can proceed. So A says energy is absorbed when bonds are formed and when they are broken. Not true. Their energy is absorbed for the bond breaking, but it's released for the bond making. So it's not absorbed in both processes, and B, it's not released in both processes. So A and B are not contenders. So then C, you just have to know, is the energy absorbed when bonds are formed and released when they are broken, or D, is energy released when bonds are formed and absorbed when they are broken? And D is the correct answer, and it's a little bit tricky because they've got the bonds forming, which is actually the second part of the process. In my mind, I would think energy is absorbed when they are broken and released when they are formed, because that's the order it happens in a reaction. Number 3, the temperature of a 2-gram sample of aluminum increases from 25 degrees to 30 degrees Celsius. How many joules of heat energy were added? Specific heat of aluminum is 0.9 joules per gram per Kelvin degree. And you will notice IB generally uses Kelvin in their specific heat value, whereas the book we used last year, the Glencoe book, uses Celsius degree. And it really doesn't matter because temperature change expressed in Kelvin or temperature change expressed in Celsius will be the exact same number. Even though Kelvin temperatures are 273 degrees different than Celsius temperatures, the change will be exactly the same because 1 degree Celsius and 1 Kelvin unit is exactly the same amount of energy. So don't let the Kelvin mess you up. So this one, you just think MCAT, 2 times 0.9 times 5. Well, 2 times 5 is 10 times 0.9 gives me 9 joules. Number 4, which statements about exothermic reactions are correct? And again, immediately in my head, I think of the graph I put off to the right, that reactants are at a higher energy state than products. They have negative delta H values. Yes, there's net energy out. Products have a lower enthalpy than the reactants. That's also true. And the products are more energetically stable than the reactants. Yes, less energy is more stable. And again, the way I remember this is that if I'm standing on one leg, that takes more energy, but I'm far less stable than if I stand on 2 legs or if I just lay down. So less energy, more stable. Number 5, a sample of a metal is heated. Which of the following are needed to calculate the heat absorbed? The mass of the sample. Yes, that's part of MCAT. The density of the sample, no. You can use the density to derive the mass, but you don't need the density. So even though we often use the density to convert our volume of liquid to the mass, It's not part of the equation, so 2 would not be considered part of it. 3, the specific heat capacity, yes. So B would be the correct choice here. Number 6, the following equations show the oxidation of carbon and carbon monoxide to carbon dioxide. What is the enthalpy change in kilojoules per mole for the oxidation of carbon to carbon monoxide? So when I look at the desired equation, I see that my first equation provides carbon solid as a reactant, and I want it as a reactant in my final equation. So my first equation, the minus x, is going to stay as is. The second equation, the CO, is my desired product, but it's on the wrong side. It's correct amount, but wrong side. So I need to flip my second equation, so my negative y becomes a positive y. So my value is going to be negative x plus y, or as IB's messing with you, the same thing would be y minus x, or letter C. Number 7, the following equation shows the formation of magnesium oxide from magnesium metal. So we've got Mg plus O2 yields 2Mg plus O2 yields 2MgO. So you notice this isn't expressed in kilojoules per mole, it's simply minus 1204 kilojoules because it's per 2 moles of Mg, per 1 mole of O2, and per 2 moles of MgO. So A, 1204 kilojoules of energy are released for every 2 moles of magnesium reacted. B, 602 kilojoules of energy per mole of magnesium oxide. That's true because they cut it in half, but it's being released, not absorbed, because it's a negative value. C, they're saying per mole, 602 kilojoules of energy are released for every mole of oxygen. No, it actually was 1204 kilojoules per mole of oxygen. There was no need to cut it in half. And D is the correct one, 1204 kilojoules of energy released every 2 moles of magnesium oxide formed. Number 8, using the equations below, which is the value of delta H for the following reaction? So again, my first equation, CuO, is the desired equation, but CuO needs to be a reactant, not a product, so I'm going to have to flip that equation. And my final equation also has 2 CuO, so I'm going to have to double it. So my 156 becomes a positive times 2. My second equation has the product Cu2O as a product in this reaction, and it's a product in my desired reaction, so I can leave that equation. And when I add those values up, I get a positive 142. Number 9, separate solutions of HCl aqueous and H2SO4 aqueous of the same concentration and same volume. So what that's telling you is concentration is moles per liter, volume would be in liters. So if they have the same concentration and same volume, then what you're really talking about is you're starting with the same number of moles. And that's important because moles will determine your limiting reactant. So they're completely neutralized by NaOH, so you've got 2 acids being neutralized by the same base, and X kilojoules and Y kilojoules of heat were evolved respectively. Which statement is correct? So, excuse me, if you've got the same concentration, same volume, you got the same moles of each reactant, what you have to look at here is HCl plus NaOH is going to yield H2O plus NaCl, but H2SO4 has twice as much hydrogen or hydronium ion in its reactant. So I've got the same number of moles of HCl and H2SO4, but I don't have the same moles of H in there. I've got twice as many hydrogen in the H2SO4. So if it took 1 mole of NaOH to neutralize X, then it would take twice as much NaOH to neutralize Y. So in other words, Y is equal to 2X. I needed twice as much NaOH, and the equation even tells me that when I write that out. I need 2 NaOH to neutralize the H2SO4. So B, Y equals 2X. 10, when 40 joules of heat are added to a sample of solid H2O at minus 16 degrees, the temperature increases to minus 8. So we have a temperature change of 8. What's the mass of the solid sample? So if I plug in the numbers I'm given, I have 40 joules as my delta H. M is what I'm trying to find. I'm given a specific heat value of 2. Temperature change is 8. So again, even without a calculator, the math is pretty easy. 40 over 16 is going to be 2.5 grams. And even if you didn't want to do the difficult math of 40 divided by 16, it's obviously less than 5. So 2.5 would be my only choice. Number 11, the mass M in grams of a substance of a specific heat capacity C increases by T degrees Celsius. What is the heat change in joules? That's just MCT, MCAT. That's the equation we use all the time, and those are the units we use. Grams, joules per gram per Kelvin, increases by TC. And again, IB is trying to confuse you a little bit by using two different units for temperature, but because it's temperature change in Kelvin will be exactly the same as the temperature change in Celsius, even though the temperatures themselves differ by 273. But if you convert both your Celsius temperatures to Kelvin, they both got shifted by 273 degrees. So the change is the same. So B and C, there's no need for adding 273 in. And C and D, the 1,000 would be if we want to express it in kilojoules. So 4 joules, MCT, MCAT is our equation. Number 12, for which of the following is the sign of the enthalpy change different from the other three? So pretty quickly, you should be able to look at B and C and know that those are both going to be endothermic, because you have to add energy to ionize something to pull that electron off. And to go from a solid to a gas is definitely an endothermic phase change. You have to heat something up. So B and C are going to have the same enthalpy change. They're both going to be endothermic. So the question is whether A is endothermic or D is endothermic. So if you look at it, in A, we've got a solid becoming less organized as a solid and a gas, whereas on D, we have 2 chlorine atoms becoming more organized as a chlorine molecule. So the way I looked at A and D is that A has got bond breaking going on as the calcium carbonate decomposes. It had to break off the CO2, whereas D has got bond making going on as the 2 chlorine form Cl2. So bond breaking is endothermic, whereas bond making is exothermic. So D is the different one. Number 12, a simple calorimeter was used to determine the enthalpy of combustion of ethanol. Experimental value is minus 920. Data booklet is minus 1370. Which of the following best explains the difference between the two values? If heat loss to the surroundings is a choice, that's always considered the number one loss or the greatest source of uncertainty or error in a calorimeter. So B. All those others would be reasonable options, but best explains heat loss to the surroundings. Number 14, which statement about bond enthalpies is correct? And this one, I didn't intend to include it on this quiz, but this one actually was a pretty easy one because you should know that bond breaking is endothermic and bond making is exothermic. So C was the easy choice. The others are wrong because bond enthalpies have larger values for strong bonds and smaller values for weak bonds, not positive and negative. They're all positive values. Bond enthalpy values are greater for ionic bonds than covalent. Often they are, because ionic bonds often are stronger bonds, but double and triple covalent bonds can also have high bond enthalpies. And D, the carbon-carbon bond for ethane and ethene. No, what you have to realize is ethane is, actually I've got this written wrong, ethane is a carbon-carbon single bond and ethene is a carbon-carbon double bond. So it's not going to have the same value for those two. Number 15, which statements are correct for all exothermic reactions? The enthalpy of the products is less than the enthalpy of the reactants. And that's true because, again, right away think reactant, products lower. This is your potential energy, or you can think of it as enthalpy. Enthalpy is energy. So it's not the change in enthalpy, but the actual energy of the products is less than the energy of the reactants. True. The sign of delta H is negative. True. The reaction is rapid at room temperature. No idea. Reaction rate has nothing to do with enthalpy. So A, 1 and 2 only. 16, using the equations below. So when I look at my desired equation, I see carbon is a reactant, and it's also a reactant in my desired equation. It's the correct amount, so it's going to stay minus 390. Mn is one of my products, but again, it's the correct amount. So I just need to flip my second equation. And so I should be able to add negative 390, positive 520, and my enthalpy change should be 130. 17, which statement is correct about the reaction below? And again, you notice it's not expressed as negative 196 kilojoules per mole because it's per 2 moles of SO2, 1 mole of O2, and 2 moles of SO3. So A, 196 of energy is released for every 2 moles of SO2 would be correct. B, 196 of energy is released, not absorbed, and again it needs to be 2 moles of SO2. C and D, they cut it in half to 98, which is correct for the SO2, but now you have to decide if energy is being released or absorbed, and it's being released since it's expressed as a negative. Number 18, which statement is correct for an endothermic reaction? So again, I draw my little sketch here and remind myself that the bond making on this side, or the bond breaking, I'm sorry, is endothermic, and over here is the bond making, and it's exothermic. Bonds in the products are stronger than the bonds in the reactants. Now, this one's a little bit tricky because it seems like they should be because it's got more potential energy. But if we reverse this equation, if you look at the two sides here, which one takes more energy to break their bonds? The reactants take a lot more energy for the bond breaking, whereas if I reverse this reaction and ran it this way, and now I was breaking the bonds in the products, they take far less energy to break. So it's kind of a counterintuitive thing there that the bonds in the products are not stronger even though they possess more energy because it's going to take less energy put in to break them because there's already a lot of energy in there. Bonds in the reactants are stronger than the bonds in the products. Yes, that's true because the bond breaking here takes a lot more energy being put in to break it. So A and B, one of those has to be true, that the bonds in the product are stronger or the bonds in the reactants are stronger. So C and D we really don't even have to consider. But if we look at them, enthalpy of the products is less than that of the reactants. No, it's more, it's higher up. And the reaction is spontaneous at low temperatures but becomes non-spontaneous at high temperatures. We have no idea. We haven't been given any information about this endothermic reaction. 19, consider the specific heat capacity of the following metals. So we've got a bunch of them given there, and it's given in joules per kilogram. That's why those aren't decimals like we're used to. But which metal will show the greatest temperature increase if 50 joules of heat is supplied to a 0.001 kilogram sample of each metal? So if I set up MCAT, the 50 joules is the delta H, 0.001 is my mass. Those two things are remaining constant. So really, it's C times T equals the same number each time. So if C increases, my change in temperature has to decrease. Or if C decreases, then my delta T will increase. So really, I'm looking for the biggest temperature change, which means I'm looking for the smallest C value, which belongs to gold at 130. And finally, number 20, one more, Hess's Law. Consider the following. So my first equation, I have sulfur on the reactant side, like I want it, in the correct amount, so I just leave the 395. In my second equation, I have the SO2, but it's on the wrong side, but in the correct amount, so I'll have to flip that. So negative 395 plus a positive 298, I would expect an enthalpy change of negative 297.